Can you tell us a little bit about the Wormbot?
You can have, populations of 30 or so animals in a small area of space. We could do 1,000 experiments at the same time. We could do 10,000 experiments. So the number kept on growing, and it wasn't this flight of imagination. It was really seeing the power of the system. There's a big set of genes that regulate aging that we haven't looked at very much at all.
The idea here is that anybody can go to the Ora website. There's a list of interventions they can pick from. So people can choose the interventions they want to test. It will get tested on the Wormbot and go into an open access database, which you were just referring to. Anybody in the world can get access to it unrestricted, right? Look, guys, if we had started this 2 years ago when I started first talking about it, we'd have an open access database now with tens of thousands of molecules. My name is Matt Kaeberlein, and welcome to the Optispan YouTube channel. Hey everyone, welcome to the Optispan Podcast. Today I am joined by Dr. Mitchell Lee, the CEO of Ora Biomedical. So Mitchell got his undergraduate degree at Western Washington University, my alma mater, so a great place to get your undergraduate at, and then went to the University of Washington where he completed his PhD studies in the Department of Pathology, did postdoctoral training with Daniel Promislow, also at the University of Washington, and then moved to industry to take on the role of CEO at Ora Biomedical. So Mitchell, thank you for joining me today. It's great to have you here and have you walk right through the door separating Ora from Optispan so we can sit down and have a podcast conversation.
Yeah, great to be neighbors and great to be here today.
Awesome. So let's start by just giving folks an introduction to Ora Biomedical. So maybe we can start with what's your high level? How would you describe Ora Biomedical at a high level? What's your elevator pitch?
So at the highest level, we're drug hunters. So we comb through chemical space, find small molecules and other interventions that can extend healthy lifespan and also fight against the myriad of different disease and chronic illnesses that are associated with aging.
Cool. Is that how you explain it to your family when you guys get together for holidays?
Pretty much,
and what's their response?
I've got them warmed up to the fact that I'm a worm farmer.
Okay.
And so, getting towards what the back end of what the goal of having the worm farm is still something we're working on. But
awesome.
Yeah.
All right. So we're going to do a deep dive into Ora, what it means to be drug hunters, why we would even be interested in longevity drugs, although I think probably most of the viewers of this podcast get that off the bat. But before we do that, let's take a step back and talk a little bit about how you got to this point. So I know you grew up in Oklahoma. You somehow ended up at Western Washington University. What happened in that intervening time to kind of shape you into the scientist and person you are today?
Yeah, that's biography is a big question. But I left Oklahoma when I was 19. My goal out of high school was to get as far away from Oklahoma and stay in the continental United States. I was from a very small town, didn't see a lot of options, didn't understand how my pathway worked in a world like that.
And had you gotten into science before that? You knew you wanted to be a scientist? Or?
Not really. I probably shouldn't have graduated high school with the math education that I walked out of there with. So I was interested in science, but didn't have some of those formal foundations that felt like it could be a live, viable option for me. Huh. And at the same time, you don't meet a lot of scientists in rural Oklahoma, so it's hard to even understand what that looks like and what that world is, the world of a scientist.
Wow. So you graduated from high school, knew you wanted to go someplace else. How'd you end up at Western?
So I got up to Western Washington through a couple of different lucky coincidences. Started doing community college at Everett Community College, learned all the math that I should have learned in high school, realized I was pretty decent at it, and that woke in me this idea, or, just kind of the realization that, back in high school, I did like science a lot.
Yeah.
I just never took it seriously because I didn't think I had a shot. It was like, oh, wow, I know math now. This is an option. And that was just a realization point to me that until that point, I had been a philosophy student, and I still consider myself a philosophy student.
Right. But in fact, one of your undergraduate degrees is in analytic philosophy, right?
Indeed. Yeah, absolutely. And so, I've always been passionate about that, but the pragmatism was always kind of on my shoulder. I didn't see a lot of want ads for philosophers. So figuring out how to move forward with that, entertaining that passion of philosophy, and then awakening that pragmatic thing that I could study science, I could engage my interest, was really the light switch that went on early before I went to Western.
No, that's great. And I ask you to, thank you for sharing that story. I ask you to share it because I think it's useful for people to realize that, there is no one path to becoming a scientist, becoming a PhD researcher in science, becoming a CEO of a biotech company, right? We all take different journeys. And I think journeys like that are really inspiring and important for people to hear. And it's really interesting how much our journeys have paralleled, right? So I also went to community college, went from my associate's degree in community college to Western Washington University, right? Not really knowing that I wanted to do science or biology until I was at community college when I, first really, I think, first of all, grew up and became an adult and started acting like one, but also really got interested in my own education and science, and the rest is history. So I just think it's useful for people to recognize you don't have to be on the PhD track or the MD track from the time you're 4 years old to actually have a productive, successful career and make important contributions. So anyways, so you then went to Western, you got 2 degrees, right? One in biology, one in philosophy, also did a master's in biology at Western. And was it while you were at Western that you first started getting interested in research, laboratory research? And when did you first start thinking about aging as something that might be interesting to study?
Yeah. So it was during my grad studies, my master's studies at Western. So I stuck around Western. I was still trying to figure out what the pathway was. By that time, I was fully immersed in biology. I was sold on the coolness of the molecular logic and genetics. Like, it was just so powerful to me. So I wanted to be there. I knew that was the next step, and I didn't know what the step was after that. Another just kind of bout of coincidence happened. I was online looking at papers and looking at research. I found a video lecture by Cynthia Kenyon. And at the time, I was studying neurodevelopment in C. elegans. So her work is in worms. So I was very impressed by that immediately. Then she started talking about this phenotype of aging. And that blew my mind.
Cynthia's an amazing speaker as well, right?
Yeah.
So,
yeah, she sets you up for it, and she can tell the story really well. But aging to me at that point was just something inert, something just kind of the march of entropy in a biological system.
Yeah.
And with Cynthia's work, you could see that there's genetic regulation that underpins so much of it. It's not just, like a truck rusting in a field is what I imagined when I was younger. There's actually a lot that you can do about it and a lot that we're learning. So it was a question I didn't realize was a question until I found it.
Yeah.
And that's always what makes me passionate.
Again, really interesting parallels, because you heard a talk by Cynthia Kenyon, who is one of the pioneers in this field, at least in the genetics of aging, and that kind of turned you from never having thought about aging to suddenly on the path that you've been on since then. When I was probably close to the same age that you were at the time that you heard this talk by Cynthia, I heard a talk by Lenny Guarente, who was a contemporary of Cynthia's and also a pioneer in the sort of genetics of aging that had exactly that same effect on me. I'd never thought about aging as something you could study with molecular biology or genetics or biochemistry. Heard Lenny give this talk about how his lab was doing that, and it just kind of shifted me onto this new trajectory that obviously I stayed on for, the rest of my career. So very cool. And so then what happened? So you heard this talk by Cynthia, you got interested in aging, then what?
Yeah, trying to figure out where I do a PhD at was the next thing. I was a master's student at Western. I'd done well at Western, so I felt like I had, the opportunity to move into a program.
And just so people are aware, Western Washington University is one of the smaller state universities in the state of Washington. So there's 2, I think, PhD granting state institutions, University of Washington, Washington State University, and then there's Western Washington, Central Washington, and Eastern Washington, which are all primarily undergraduate universities, but they do have small master's graduate programs, just for context of why you couldn't just do your PhD there.
Yeah, exactly. Yeah, smaller, kind of more teaching-focused institutions, small graduate program, enough for you to dip your toes in and figure out if you like it or not, if that's the world for you. I did it, realized that it was, and it was then figuring out who was doing biology of aging research. I knew I wanted to keep working in invertebrate systems because the power of that system, when you're kind of indoctrinated into it, I'm a full believer.
So again, you were working in C. elegans at that
yes,
time,
I
right?
was. I was doing worm neurodevelopment research, and the genetics that you can do in C. elegans, the power of the system. I knew that's where I wanted to stay. I knew there was a lot of power, if not in that kind of system, in similar systems. Sure. And so I was just looking up and finding names and learning about what work people were doing. And, came across, Cynthia, Anne Brunet, came across Brian Kennedy, and then came across your name. And it was like, wow, this guy's doing something really cool. And then, just all these coincidences again happen. It's like, wow, he's at UW. I don't want to leave Washington. You've learned by now that, I came up here from Oklahoma. They're going to have to drag me out of this state. I love Washington so much. So you were at UW. UW is a world-class research institution. I learned more about the aging strengths there, right. Learned more about your research. And I was just kind of hooked. It was like, wow, okay, right time, right place, right opportunity.
Yeah, and I mean, UW has been a leader in the field of aging research for 20 plus years now. So kind of a really fortuitous situation, right? That there was this opportunity to study the biology of aging, stay in Western Washington, come to University of Washington, and so you joined the pathology program at UW. I don't remember whether that was yet the M3D program or was it still the...
It was still pathology at that time.
Okay, so we're getting a little off in the weeds. But, anyways, joined that program. You ended up doing your PhD jointly with myself and Alan Herr. And unfortunately, Alan suffered from cancer for many years and passed away in 2021. I know he was a very important mentor to you and to many people at the University of Washington, a great loss. It's up to you, but is there anything you want to say about how Alan impacted you and your growth as a scientist and as a person?
Oh, he helped me grow as a scientist, absolutely. Some of those, he was always so impressed by the genetic experiments from decades ago where they just had nothing but logic to hang their research on. So those kind of genetic tests. I can't think of one just off the top of my head, but he was always impressed by those. He taught me a lot about how to be a good person, how to deal with adversity, how to, just try to be calm. And, you learn a lot of things from a mentor. I wasn't expecting to learn everything that I learned from Alan.
Yeah, I mean, I agree. Alan was one of the best people probably that I've known, like just as a human being, really great guy. And unfortunately, it seems like the best of us are taken too soon, too often. So a huge loss. But I feel very fortunate that I got to know Alan as a colleague and got to know him, as a joint mentor for you during your PhD thesis. And you had sort of a unique PhD thesis where you were working in budding yeast, right? So another, simple model organism that you can do very powerful genetics and molecular biology and biochemistry experiments. And your projects, you had sort of different projects in the two labs, but they were kind of connected by, the idea of I think understanding the role of genetic variation in Alan's lab, strongly influenced by mutation in a variety of processes, cancer in one obvious case, aging in another case, and particularly the work that you did, in my lab, I think sort of set the stage for what you've gone on to focus on, which is really the sort of pharmacogenomics of aging, right? This interaction between genetic diversity and drugs, small molecule interventions that can impact longevity. So maybe you can just talk a little bit about, what that means. Why is it important to think about this interaction between genetics and and aging and genetics and interventions that might affect aging.
Yeah, absolutely. I think it's one of the biggest underexplored areas right now in the biology of aging is thinking about how natural genetic variation impacts how we age and also the efficacy of these interventions that we ultimately come up with. There's some really great studies that have shown, even things that seem to be very robust, like caloric restriction. Yeah. If you look at caloric restriction across natural genetic variation or different types of genetic mutants, not everybody benefits. Not everybody benefits all the same, in fact. There are some groups that have very a low rate of return for those interventions, and then there are some, I think, which is really exciting, that reap a bigger benefit.
Right.
So there's, extending healthy lifespan and fighting aging for everybody is absolutely the goal. But it seems like in some of those studies, it points at the glimmer that we could be helping particularly shorter lived individuals right now with these therapies. Yeah. And that was always a big driver of my interest.
And then you went and did your postdoctoral work with Daniel Promislow, continuing to look at genetic variation and its effect on longevity, and in particular response to rapamycin, which is a huge topic of interest, obviously, in fruit flies this time. So you really have spanned the sort of common invertebrate model organisms that are used to study aging and a variety of different areas of biology. Do you want to just briefly talk about that work and what you were interested in and what came out of that?
Yeah, that's a really cool study. So that's another one. In flies, they've got these large genetic diversity panels. And yeast, they've got some elements of that. Actually, Alatin Kaya did a lot of kind of putting a bit of that together and thinking about it with aging. In the Drosophila side, they've had some of these panels for a little while longer. And so I was curious about rapamycin efficacy.
Yeah. So this panel is the DGRP panel?
It is, yeah.
Drosophila
genome reference panel. Yeah.
So again, just to give a little bit of context, these are lines of fruit flies that were caught in the wild. It was like at a farmer's market right?
Yeah.
And they've been sort of extensively characterized in the sense that they're fully genome sequenced, and people have done a variety of different types of additional characterization of transcriptome, proteome, metabolome. So we know a lot about each of these individual lines. How many are there? Do you remember?
Just a little over 200.
Okay, so there's like almost a little more than 200 different wild-derived strains, lines of flies that have all been extensively characterized. So maybe you can just comment on, before you talk about what you did, what does that give you? What sort of power does that give you for, why is that important? Why is that useful from a resource perspective?
So between those 200 lines, it captures about 1 million different single nucleotide variations. So it's a deep sampling of natural variation. And like you said, what's interesting about it is it was all collected from just one farmer's market. So that gives you kind of an intuition about the breadth of genetic diversity that's in Drosophila, and maybe kind of, an inkling towards the genetic variation that we're not thinking about as much in humans and mammals.
Right. Yeah, I think that's super important. And, we often study things in one inbred genetic background in mice, for example, and then try to extrapolate that to the, extremely complicated genetics of humans, not to mention all the environmental variability. So just from a pragmatic perspective, though, my understanding is one of the really powerful things you can do with these lines is you can then look at how they respond to different changes, for example, in the environment. So just to take caloric restriction as an example we were talking about, Daniel and Pankaj Kapahi and others have looked at the DGRP lines and subjected them all to caloric restriction. And like you were saying, some of them have their lifespan extended, some have no effect, some actually have their lifespan shortened. The power you get with those lines, though, is that because they've been fully genome sequenced and we know a lot about other aspects of their physiology, you might get some hints immediately about potential mechanisms. So you can really quickly get from observation of phenotype to hypothesis about which genetic variants might be driving that sort of difference in response to something like caloric restriction.
Yeah, that's definitely the goal.
Yeah, not as easy as it sounds, but nothing in life is. So.
Yeah, with the rapamycin study, what was so cool about it.
So what did you do with the rapamycin study?
Yeah, so this was, instead of looking at lifespan across this panel of 200 flies, we wanted to look at something even a little quicker than lifespan. So lifespan in a fly is fast compared to a human. It still takes months, though.
About 3 months, right?
About 3. Yeah. So what we wanted to look at was development. We wanted to just look at some kind of mTOR responsive physiological readout and then look and see how rapamycin impacted that response. So developmental timing is what we set out to choose. And flies develop over a course of about a week under natural conditions. With rapamycin, you can delay it. The typical delay is like about a 1-day delay in their development. Easy enough to measure, very reproducible. TOR signaling in development is really where it seems like TOR signaling is very highly evolutionarily honed, so you see effects fast.
Right. And so mTOR is getting turned up during this dramatic growth period of development, and rapamycin, of course, turns down, inhibits mTOR, right?
Yep.
And so you're looking for variants that respond differently.
Yeah. Very intuitive. Something that would extend out the length of development time because you're turning down cell growth, cell division.
Right.
And we found a lot of those that did that about how we expected. We found some that were very sensitive. So, instead of taking 7 days to develop under normal conditions, it took them twice as long, 14 days to develop.
And were you treating with a dose of rapamycin that slowed development, or were you treating with a phenotypic dose of rapamycin?
In the wild type strains, you get about a 15 to 20% delay in development.
So did you find anything that was resistant then that did not respond to rapamycin?
That's the wild thing, is we found some lines that were, no change whatsoever. There are a couple lines in that DGRP panel where development is ever so subtly hastened.
By rapamycin.
By rapamycin treatment.
Yeah.
We still don't know what that means.
So, this is obviously fascinating, and my mind immediately goes to what's the mechanism, right? Yep. But I think this is useful just at a conceptual level for people to understand. This is really the beauty, power, complexity, and in some ways frustrating aspect of genetics, right? Is that, you get, when you do this sort of unbiased genetic screen, you get all of these different outcomes, right? And this just really, I think, emphasizes the point that we have to be very careful with one-size-fits-all recommendations, right? Because what you're saying is, you had some that looked just like you would expect them to look when you treated with rapamycin. You had some where development was delayed even more than you would expect, presumably sensitive to rapamycin in some way. You had some that were completely unresponsive, at least at the dose that you tested. And then you had some where you got the opposite phenotype, right? And I don't know that you would expect to see that in very many people, but there are probably some people where, you're going to have outliers that respond the opposite of what you would expect. And so we have to be cognizant of that, and obviously would like to understand that better, not just with rapamycin. This is true with almost any drug or supplement or other intervention that you might think about.
Absolutely. No, that's one of the things that worries me a little bit with where the field is right now. There's so much enthusiasm, but we really don't have points on the board yet in terms of an intervention we know works for humans. Even when we do, there is going to be genetic variation that we have to contend with. And all the while, you hear stories about people and their stacks of, handfuls of different natural products and small molecules. And I don't know if any one of those is good on its own, but I can almost guarantee all of it together is not probably going to be good. Like it would be very surprising if you found the right cocktail just through this kind of it almost seems like a grab bag effort. I wouldn't.
Yeah, no, I hear what you're saying. I think I tend to agree with that. I've often said that, when you start just randomly changing things in any complex machine, you're more likely to screw it up than make it better.
Yep.
But I also think, I agree completely with what you're saying. I also think, there's got to be some middle ground, right? In terms of, we can't be paralyzed by the fact that we don't understand the system well enough to perfectly predict an outcome. But we also need to recognize that there is going to be individual variation in the response to anything that we do, not just in the longevity field, any medication, really any intervention. I mean, I think that diet is a really interesting place to think about this, right? Yeah. You think about some of the fad diets that are out there, or even some diets that maybe aren't fad diets that actually do have benefit for a subset of people. But we don't necessarily know at the individual level which person is going to respond positively, indifferently, or negatively to a particular dietary regimen. So again, it's just the system is immensely complex, and I think this is a good case example where you can see every outcome possible in just a genetically diverse line of fruit flies. And you have taken out the environmental piece, which also adds a huge amount of variation, right? So this is in a laboratory where the environment is pretty well controlled for. Then we take that out in the real world and, all bets are off. So it's just worth appreciating, that complexity. And there's a probabilistic component to anything that we do, and there's no guarantees, I guess, when it comes to the way your specific genetic and environmental makeup is going to respond to rapamycin or anything else that you do.
Yeah, results may vary.
Which is why biomarkers are so important, right?
Yeah. Well, and I think there is a lot of value in doing those, individuals who are doing a little bit of the N of one kind of studies, things like that. If those individuals, capture the data, collect the data, be really rigorous about it. And I think there's value in those data sets. And I think we will learn things from them.
I agree with that. Yeah. So you were actively doing this research on response to rapamycin and developmental timing in Drosophila. Presumably at some point you started to recognize that, maybe academia wasn't the path for you. I guess I didn't ask. Up till that point, had you sort of seen yourself on the academic path? Or had you already started to think about going, in a different direction, maybe into industry?
No, I was a dyed-in-the-wool academic. That was my pathway since starting in grad school. It was during the time in the lab at first, when I realized that, I'm not really getting to do the exact kind of science I want to do. I'm super compelled by mechanism. I love it, but I'm kind of a weird scientist in a lot of ways. I kind of just want a system that works and something that I can turn the crank on and get a lot of outputs from. I know how the system works as best as I can make it work, and I know what the outcomes are. So that's how drug discovery and drug development was really compelling to me.
Right.
Like, I want to do a ton of lifespan experiments, and I want to just see what drugs work. And so at that time, if you tried to get a grant around that, you'd be accused of going on a fishing expedition, or if you wanted to test a drug across natural variation, you'd be told you're only doing descriptive science. And it was just, I was seeing that the kind of science I wanted to do wasn't being supported as well as I thought it should be in academia.
Yeah, absolutely. And so, this, in many ways, sounds like a right place, right time, right opportunity, because this was about the time that we had developed the Wormbot in my lab, and we'll talk more about the Wormbot in a minute. And many of the same frustrations you just talked about, with very difficult to get funding for large scale sort of screening approaches to what people would call fishing expeditions, right? Non-mechanistic, I guess, kinds of studies. And so then we sort of, in conversations, you and I talked about, maybe spinning out the Wormbot into its own company, and came up with Ora Biomedical. And you took a leap of faith and jumped over to the company along with Ben Blue, and the rest is history. So maybe let's go back to Ora Biomedical and talk now in more detail about what's happening at Ora and kind of the thesis behind it. And I want to hear you, in your own words, talk about, why Ora, why is it necessary? I think you've heard me talk about how I was very frustrated by, this idea of intervention stagnation in the field, and the fact that we're not finding new interventions of bigger and better effect size. And so that's certainly a part of the Ora rationale. But maybe in your own words, you can talk about, from your perspective, why do we even need an Ora Biomedical?
Yeah, no, that's a great question. So What the best way to think about that is just kind of thinking about the state of drug discovery right now in longevity medicine. We've seen the potential in the lab time and time again of interventions having this impact, being able to extend healthy lifespan and fight across so many different diseases. To see how widely utilizable they are in the lab is, it's so compelling. And so the question is, why aren't there more of these? Why haven't we advanced these things further? Why don't we understand this world better? And so that was really, for me, the impetus to drive Ora Biomedical was, wow, we're at the cusp of something really important. And it doesn't seem like people are thinking about small molecules and interventions as much as they should in this space. It's definitely not translating in the way that it needs to. So how do we make that happen? And how do we accelerate that? Mm-hmm. As an invertebrate geneticist, somebody who sees the value of those systems, it's like, okay, well, let's screen through as much as we can as quickly as we can. Pick all the low-hanging fruit, start doing things about in realms of combination studies and start better understanding how these things work together, and then start translating them forward. But, starting with some foundation, some animal model, some system that you can start to understand the pharmacology of aging very comprehensively in, and then move forward from there.
Yeah. Yeah. And actually, this might be worth just taking a minute to talk about. You said this, the pharmacology of aging, right? I think a lot of people don't actually realize how little that space has been explored. So, I think the largest, at least public database of interventions that have been tested for longevity, lifespan, is drug age. Mm-hmm. And it has 2,000 something like that.
Yeah, a little less, yeah.
A little less than 2,000. And that's the sum total of knowledge across not just C. elegans, but all of the organisms that are commonly used in aging research. So that's not a very big number when you think about the number of small molecules that are out there. And when you start talking about combinations, right, even two-way combinations of 100 individual molecules is way more than 2,000, right? So very tiny fraction of the intervention space that has been queried. And I would agree with you. I would say that it doesn't seem like there is much happening in the discovery of new interventions in the field over the last 10, 15 years. It seems like a lot of people have very narrowly started to focus on mechanisms and the hallmarks of aging, which is important. Mechanistic understanding is important, but at the expense of finding new things that work better.
Yeah, it was almost to the point when I was in my grad studies, to even discuss a non-mechanistic science project, you weren't really doing science in a certain kind of way. Yeah. It's like, well, no, I mean, it's good to describe things also. It's good to just, find out what does, things, and then you can move into mechanism.
Right. And when you can look at a large enough scale, you're always going to find cool stuff that you didn't expect, right? Yeah. Going back to the rapamycin story in Drosophila, right? That's my favorite part of unbiased genetics, right? Is you find things that you completely didn't expect. And that's how you learn brand new stuff that nobody ever knew before. So anyways, I think we share that sort of mindset and vision of, the importance of doing unbiased discovery science and at scale whenever possible. So let's take a minute before we talk about what Ora is up to now and just talk about the Wormbot, because that's kind of, the foundational tool that Ora is using, at least in this phase of its work. So can you tell us a little bit about the Wormbot, what it is, how it works, and how Ora is applying that right now for massively high-throughput longevity drug discovery?
Yeah, absolutely. So the Wormbot works with populations of C. elegans, so a small little roundworm. You can culture them in 12-well dishes, so you can have populations of 30 or so animals in a small area of space. So what the Wormbot does, it's a video imaging and tracking platform that takes pictures of the populations, videos, and then does phenotypic calling and tracking. So it can not just say where the animal is, when it's moving, it can start to get things related to rates of speed, acceleration, behavioral changes, and that's the neural net side of it, which is a phenotype describing process, essentially. So we've got a video platform that measures the populations from life and day one adult until death. So you've got all of this rich information of drug-treated animals, and then you learn things by looking at the videos and the data to get things associated with movement, behavior, health, in addition to survival.
Right.
So,
and this is all robotic, right? So once the experiments are set up on the Wormbot, basically a human being doesn't have to do anything else. I know Ora is doing things a little bit differently now with cycling experiments on and off the robot to maximize throughput. But even that's a very minimal human effort. And it might be worth just comparing that to what had to be done before the Wormbot was in use. So I don't know how many C. elegans lifespans you actually ended up having to do.
Very few.
But it involves, I did a lot, not as many as yeast replicative lifespans, but I did my fair share of C. elegans lifespan experiments. And, that used to be an experiment where human beings had to every day for one of those plates. So the Wormbot each robot holds 144 of these experiments. If you were doing it manually, you'd have to go to the incubator, get that plate out of the incubator, put it on a microscope, sit down at the microscope, look under the microscope, count the worms, and count how many worms were still moving and how many worms were not moving. It's even worse than that. The ones that weren't moving, you actually had to take a little wire pick, which is like the equivalent of a telephone pole in a human being, and tap the worm on the head to see if it would move when you tap it. And if it didn't move when you hit it with the telephone pole, then you counted the worm as dead. And you had to do that every frickin' day until every frickin' worm on that plate, when you hit it with the telephone pole, didn't move. So it was very nice to have a robot where you could just put the plates on the robot would move the camera, take a picture, take a movie, and then let the neural network tell you whether the worm was alive or dead. So it's a very efficient approach compared to the way we had to do things in the past.
It's efficient, and it's a lot more robust too, because we've got the videos, we've got the data. You can just always go back to the actual raw source.
Yeah, I was just going to say that's a point that's worth amplifying, is the data integrity piece, because this is all video or still image data that is captured, and you can put a timestamp on it, and there's really no question of human bias, at least. I think there can certainly be bias in the neural network and the way it calls worms and things like that, but you can always go back to the data if you get a hit or if you get something that looks odd, and confirm or refute what the neural network called and what the effect was reported to be. So it's actually very powerful from that perspective in terms of rigor and reproducibility.
Yeah. Yeah. Well, and the things you can discover are really cool. One example that comes to my mind, there's a drug that we're testing right now. If you just looked at survival curves, it would look like it's extending. And kind of an impressive extension too. It's only when you dig into the data that you start seeing that there's a lower number of animals in the treatments. And then when you actually look at the videos, you see that a substantial amount of those animals are leaving the population. So they're moving away from the wells, where you're just biasing the population. That's actually a compound that is creating a fleeing phenotype, not a longevity phenotype.
Well, so I would push back on that a little bit. I would say that it may be the case that you're biasing the population. It may also be the case that it's causing two things to happen: the fleeing phenotype and a longevity phenotype.
Yeah.
Right. And it could actually be biologically that those two things are somehow connected. In other words, the same signaling pathway that regulates foraging might also regulate longevity. And there's actually some reason to think that could be the case. So, but I think this is a really good example of where, you have to be very careful. There are artifacts that could creep in, and this is a nice system in being able to detect those artifacts, whereas a human being, I think, would recognize there were fewer animals on the plate, but wouldn't be able to go back and then by looking at the captured data, figure out why there were fewer animals on the plate, right? That, in fact, they started with the same number and they all foraged their way off the plate, right? So super interesting. And we see things like that with food consumption, right? There are certain drugs that maybe cause the animals to consume more food or less food. That can affect longevity. So these are all things that can be teased out. And it's really nice to have the video evidence that you can go back to and tease out what's going on. Contamination is another thing. If you get a mold spot on your plate, you're going to see it in the video or the still images. So it's very powerful from a rigor and reproducibility perspective. Okay, cool. So the Wormbot, like I said, each Wormbot can do 144 plates at about 30 animals per plate. So that allows you in an automated way on one device to do, what are we talking about, 4,000 individual lifespans without really any human intervention being necessary.
Yep.
And with improvements at Ora, you guys have increased that by about fourfold per device. So you can start to get up to some pretty impressive numbers in terms of the number of experiments and number of individual animal lifespans that can be recorded in a reasonable amount of time. So we'll come back and talk about this idea of a 1,000,000 molecule challenge and testing 1,000,000 interventions. Before we do that, though, I know one of the questions that you get asked a lot, I get asked a lot is, can we really believe anything that we get out of C. elegans, right? So maybe talk a little bit about C. elegans as a model for aging research and what we know and what we don't know, and why you think it is that C. elegans is a good model for doing these kinds of high throughput longevity discovery experiments.
Yeah, absolutely. No, that's something I'm sure you've heard it, just as much as me, definitely. But, C. elegans are so different. They're so seemingly disparate looking from humans. What could we possibly learn about human aging or human biology from something like that? Actually, quite a lot. Really, when we think about aging isn't something that just automatically manifests in a tissue outside of a cell or a molecular context. It goes all the way into the cell and the molecular and these subcellular, submolecular processes that break down. That breakdown starts to reverberate out, impacting cell health, which impacts tissue health, organ health, which is really what I see as the major driver of aging. This molecular level destabilization that reverberates out. And so at that molecular level, when you look at a worm cell and a human cell, you can't tell the difference between one or the other. They've got all the same subcellular features. They've got a lot of the same pathways. The things that break down with aging aren't just these molecular features. They're also features that are pretty fundamental to life. Nutrient signaling, protein translation, things that nature didn't solve that problem more than one time. The protein translation machinery in a worm cell is identical by and large to ours.
Yeah.
A lot of the same things with nutrient signaling as well. Yeah. So aging happens at the molecular level and highly evolutionarily conserved processes. And because of that, we can learn from worms and translate to humans.
Right. And even many of the hallmarks of aging are conserved in worms. Many of them were actually discovered from studies in worms.
Yeah, that's the humbling thing, too. It's like the more you engage in the aging literature, the more you're going to realize a lot of things come back to these little nematodes and yeast.
Yeah, we talked earlier about how seeing Cynthia Kenyon's video lecture inspired you to get interested in aging. And, Cynthia, along with Tom Johnson and others, Gary Ruvkin, really fleshed out the importance of insulin IGF-1 signaling as a longevity pathway in worms. And by and large, it turns out that's probably one of the most important longevity pathways in mice, in dogs, probably also in people. There's some evidence now that mutations in that pathway affect longevity in people. So, there's no question, I think, that at least many aspects of the biology of aging are conserved between worms and humans. Not everything, but a large fraction. And we now know of several genes and pathways that affect lifespan and apparently the rate of aging in worms that seem to have a similar effect in fruit flies, in mice, and in some cases, even some evidence in humans. And so, it's frustrating to me that we still have these boneheads who argue that, you can't learn anything about aging in people if you don't study aging in people. It's like, or even these people who ask whether, aging in C. elegans overlaps at all with aging in mice. It's like, do you know the literature?
Yeah.
Obviously it does.
Yeah.
There are many examples.
When people are like, well, give me an example of how C. elegans relates to human aging. It's like, well, aside from insulin, metformin, rapamycin, mTOR signaling, mitochondrial dynamics, like AMP, aside from those.
and 8 out of 12 or 10 out of 12 hallmarks of aging. Yeah, right. Again, obviously, we don't know whether any given intervention is going to have a big impact on human aging, but that's true across the board. It's not a C. elegans thing. And I think you and I are just expressing some of our frustration with the fact that this question has been answered in the literature, and I think it's a legitimate discussion to have whether we still have new things to learn about aging in C. elegans or interventions in C. elegans. I don't think it's a legitimate discussion to have whether there are aspects of aging that are conserved in C. elegans or whether finding drugs that extend lifespan in C. elegans is likely to also tell us about drugs that extend lifespan in at least mice.
Yeah.
People, it's hard because nobody's proven that you can extend lifespan with the drug in people, at least across the population. So anyways, I think it's a done deal, and people who still ask that question should just go learn the literature and shut the.
Yeah, you got to do the homework, like it's, like, all right, you feel that a worm is different from you. Like, that's cool, but,
So what about this question of, is there still anything to learn? Like, in other words, people have done RNAi screens in C. elegans, tested across the genome, effects for lifespan. What makes you believe that hasn't already told us the story, right? That we've already done what we can do in C. elegans, and we should move on at this point.
Yeah. The genetic side is compelling with regards to what we can target. So we can't target all the areas of the genome in the same way with the genetics that were done. So that's what I would say is a big limitation. So, that's thinking about stuff that, I know you've been thinking with Alati and Kaya about this a lot. There's a big set of genes that regulate aging that we haven't looked at very much at all because they're hard to get at, because when you modulate them, it kills the organism.
Yeah. So essential genes and is one sort of extreme example of that, where an essential gene just means it's essential for life. If you knock it down too far, by definition, lifespan becomes 0 because you're dead. And so, those are hard to study in the context of aging.
Yep, that's a difficult one. So there's subsets of the genome that we haven't explored there. So I think there's some to learn so far just in that space.
Yeah. And I would add to that in every organism, but C. elegans in particular, all of the genetic studies, other than a very, very tiny fraction, are knocked down. So I mentioned RNAi for people who aren't C. elegans aficionados. RNAi was a tool that was developed in C. elegans many, many years ago now. And it's a really powerful way to turn down the expression of almost any gene in the genome very easily experimentally. But you can't turn it up. And so we can't look at increased function for individual genes. And most of these experiments have been done in very sort of crude ways, even with RNAi, where we don't really know how much we turned the gene down. And so even if we just think about the genetics, it's a tiny, tiny fraction of all the possible doses and levels of function you could get for any given gene. Which I think actually raises, this is a bit of a you're a philosopher, so maybe you'll like this, a philosophical question, which is, people ask the question, like, how many genes in the genome affect aging, right? Is it a small percentage? Is it a large percentage? I don't think we know. I don't know if you know off the top of your head. I feel like the percentage from RNAi screens is around 3.5% of the genes when you knock them down with RNAi might increase lifespan. There's some noise in there, and so that, I don't know if you think that's a big number or a small number. I think a lot of people were surprised that it was actually that common, that when you knock a gene down, you would increase lifespan. But I think maybe more interesting question is, has any given gene expression function been optimized for longevity?
Yep.
What do you think? I know what I think. What do you think?
No, I don't think so. I wouldn't want to go too far into the weeds, but that's kind of my next point, is about combinations and what we haven't explored. Once you've got something extending lifespan through one pathway, what's the next pathway? What's the next way to modulate?
Okay, let's hold that, because that's super important. Because when we think about how much even of the genetic space has been explored, when we start thinking about combinations of genetic perturbations, all bets are off.
Yep.
But this question of, for any given gene, has its expression been optimally tuned for longevity? I think the answer is probably no, because longevity is not selected for, right?
Yes.
Reproduction, passing your genes on to the next generation is really where all of natural selection acts. So I would speculate that none of the genes in our bodies or in a C. elegans have been optimized in terms of expression or function for lifespan per se. And if that's the case, then it becomes an interesting question. For any given gene, could you find a different level of expression or function that would increase lifespan?
Yeah.
I don't know the answer to that, but it might be a much larger fraction of the genes than we appreciate right now, that if you could explore that entire space of genetic perturbation, would actually lead to a significant increase in lifespan. Maybe it's 20%, maybe it's 50%. I don't know.
No,
might be a really big number.
I would agree with you there. Yeah, I wasn't picking up on where you were going with the evolutionary point, and thinking about, the genetic structure we have is not meant to make us live for a very long time. Right. The genetic structure is honed to pass on the genetic structure.
Right.
And so we are... I don't think it's solely shaped by development. I do think there are perhaps interesting aspects of primate evolution that have created some later life selection.
There may be some
pressure.
selection, like kin selection for parents, grandparents, things like that. Sure. Absolutely. Yeah.
So I totally agree. I wouldn't put everything in the development. It's all just an evolutionary consequence of development camp with humans, but I would also totally agree with you as well.
So this all raises the, I think, important point, though, that even the genome-wide experiments by RNAi that were done really only looked at one level of expression for each individual gene that was always lower than the normal level of expression. So no overexpression, really. Yeah. So now let's talk about combinations, because that adds even more complexity to the situation. So where were you going with that?
So with the combinations is, that is the cutting edge right now in the literature, is seeing these studies looking at putting drugs together and seeing additive and increased effects. Right. That should not... We should not be at this level right now. We should have already figured out a lot of those combinations.
Well, even in the genetic space, the number of combinatorial experiments that have been done is pretty small. I mean, people did a lot of early, what are sort of the equivalent of genetic epistasis experiments, where you have a mutation that increases lifespan, you have another one that increases lifespan or that shortens lifespan. You make a double mutant and you look at the interaction. But by and large, it's a pretty small fraction even of that space that's been explored. And I would venture to guess that if you looked at all of the genes by RNAi that increase lifespan in C. elegans, that have been reported to increase lifespan in C. elegans, very, very few combinations have been studied even there. Those are the obvious experiments to do. Very, very small fraction of that space has been explored on the genetic side, let alone the small molecule pharmacological side.
Yeah. That I think speaks to the question itself. Is there more to learn? On the combination side, we are so far into the weeds with it.
And here's the thing, right? We know there are examples where you can combine two genetic mutations and get additive or apparently synergistic effects. We know those exist. Why haven't we gone and found more of them? So this is the question: why haven't people looked? Genetically, pharmacologically, why hasn't this been done? And I think this goes back to what we were talking about before, largely because, at least in the current environment, funders won't fund people to go on fishing expeditions and find really cool shit. Yep. Because that's not mechanism driven. This all sets the stage for why Ora. Why do we need a platform where we can actually look for new, more potent longevity interventions at scale?
Yep, absolutely. Yeah. If you think about all of the drug discovery, and if you lumped in all the genetics as well, maybe we've screened or tested, a couple 100,000 types of interventions of all different sorts, different perturbations. Chemical space has millions and millions of chemicals and small molecules in it. So, there's so much more room for us to look at that we haven't looked at.
And I would venture to guess that even if it's been a couple 100,000 that have been screened, the majority of those were not screened in a quantitative or reproducible way.
That was the one thing I was going to piggyback on, talking about the RNAi results. It's like, screens, we also know, aren't necessarily meant to create a large, rigorous, excellent data set. They're meant to find hits that you then follow up on. So the quality overall of a screen, you have no idea of how good it is. You only know that you found something that you can move forward
Right.
on.
And I think there's been very little in the way of attempts to replicate and reproduce a lot of that data. Although, again, in the case of the RNAi screens in worms, we have the advantage that at least more than one lab has done a genome-wide screen. We have the disadvantage that the overlap was very small between those screens. I don't know what that means, other than there's a lot of noise in the system. So even of the things that are, I think I was careful and said reported to increase lifespan in C. elegans, we don't actually know much about the actual rate of true positives there. So lots to be done. Okay, so that brings us to the million molecule challenge. And so I think we've kind of set the stage for why we would want to look at a large number of interventions. We've hopefully established for people that hasn't really been done, certainly not in a quantitative, careful way. The Wormbot technology gives an opportunity to do that at a large scale in a quantitative, careful way. So how did we get to the million molecule challenge? What is that, and how did we get there?
Yeah, so I think while the Wormbot was still in your lab, people were seeing the potential, the power of it. These ideas of, wow, we could do 1,000 experiments at the same time. We could do 10,000 experiments. So the number kept on growing, and it wasn't this flight of imagination. It was really seeing the power of the system. And once we got our hands on it at Ora and brought it into our own location, figuring out how to continue to scale on that platform was one of the first things that we did. So a few little methodological tweaks, building a little bit more apparatus.
I would say it's a little more than that. So it's kind of funny thinking back now to the first iteration of the Wormbot, right, which was actually built with a make block kit that you could buy on Amazon by Jason Pitt, who you know well, who's a super brilliant guy. He came up and developed the Wormbot. But thinking about that first iteration to where the technology is now is kind of mind-boggling. And so it's gotten a lot better.
Yeah. So, as we're continuing to scale and learn and figure out what the bounds are that we can push, this number of 10,000, 100,000, well, damn, with this technology, we could probably get 1 million molecules done, and it wouldn't be, this Herculean decades-long effort. It wouldn't be a giant resource sink. Honestly, for a pretty reasonable price point, you could test 1 million molecules in under 5 years with this system. And that's what we were starting to see congeal, and that's really what gave us this, this banner slogan of the million molecule challenge as we've started talking about.
Yeah. So just to give people an idea of where the technology is at today, the improvements that Ora has made, what would it take to actually measure quantitatively 1 million interventions for their effects on lifespan in C. elegans?
Yeah, for that, we could do that work in under 5 years with the right kind of resources. And this isn't, billions of dollars. This is actually a very, for the cost benefit, I'd say it's an incredible cost benefit for what you get out of it.
So I obviously see the power of having data on 1 million interventions. And I want to just clarify something, because I think some people sometimes get confused about this. We call it the million molecule challenge. It doesn't necessarily have to be 1 million individual molecules, right? That's why I keep saying interventions. Could be combinations of molecules. It's also worth just stating explicitly that Wormbot technology is really agnostic to what the intervention is. So if you had a library of, say, gene therapies, genetic interventions, and a way to deliver those to C. elegans or create a library of strains, you could also look at genetic perturbations. You could look at other environmental perturbations. The Wormbot doesn't care.
Nope.
So we are, for now, most interested in small molecules, I think, but there's no reason to necessarily constrain ourselves to small molecules. But regardless, we'll say the 1 million molecule challenge, but it's really 1 million interventions. And I know you're thinking about combinations as making up much of that space, right?
Yeah, combinations, dose response studies, things to, not just get at a large number of interventions, but create the most consistent and rigorous database that's ever existed of its kind.
And what will we be able to do with that database?
So, the first thing is getting hits out of it. You'll find new interventions that extend lifespan. You'll also find potentially new things that are contraindications to lifespan as well, which could have an interesting value to them.
Yeah, I keep saying Ora's going to corner the market on anti-helminthics.
Yeah, the next generation of them. Yeah. So no, we can totally do that. Just
to give a funny story, right? I know you know this story, but when we first started working with the Wormbot and FDA-approved drugs in the lab, we were just doing a very small pilot screen. I think it was like 100 or something like that. And this was in the early days of the pandemic. And we found this drug that had this really strong effect on lifespan, except it shortened lifespan from like 20 days to 1 day, right? All the worms were dead in 1 day. And I'm like, Ben, what is that? And he goes and looks, and it was ivermectin. And this was right at the time that ivermectin, was a very hot topic because of the pandemic. And I was like, oh, thank God we did not find that ivermectin extended lifespan. That would have, well, who knows? Maybe that would have been good. But it was a nice confirmation that the system actually is working, because what is ivermectin, right? It's a dewormer, right? It's an anti-helminthic. So it's a nice positive control that, in fact, we did get a hit in the opposite direction for what we were hoping for that actually made sense.
Yep. Yeah, and highly effective too.
Absolutely.
If we find a
it
better
is a very
ivermectin,
potent dewormer. Yeah. I don't know what effect it has on COVID-19, but I do know it is a potent anti-helminthic.
Yeah, it's great for that.
So you were talking about what the value is of a very large database.
Oh, like yeah, this. Yeah. So, the hits, the things that you get out of it as a top level is, one obvious thing. What we're also creating, like I said, this is going to be the world's largest and highest quality longevity interventions database. So we're going to have something that I think predictive AI is going to be incredibly powerful to point at. Because, right now, you've talked about, the dearth of intervention studies that are out there right now. They're also widely skewed, too, where you're only getting subsets of the data. You're typically only getting the data for the things that work. Yeah. So you're missing so much of the landscape of pharmacology of aging that we can find.
And this is actually, I think, an important point, because, there are people who are taking sort of the obvious approach of saying, okay, we've got a long list of things, maybe not a long list, we've got a list of drugs that extend lifespan. We go to Drug Age. Anybody can go to Drug Age and download what's been reported to extend lifespan out of Drug Age. We can use AI based on what we know about these drugs to predict new interventions that might extend lifespan. And that makes perfect sense. Again, very intuitive approach. The problem I think that you're alluding to is that we've only explored such a tiny fraction of the intervention landscape, and it's very biased towards certain pathways, that's a very poor training set for that kind of a predictive AI approach. I would layer on top of that, I don't think we really know, even among the drugs that are listed in Drug Age as extending lifespan, how many of them are real, how many of them are true positives. I know that Ben at Ora has done a little bit of, trying to validate things that came out of Drug Age and ask, in the Ora system, can those things be reproduced for their effects on lifespan? And it's been somewhat disappointing, I would say. I don't know what the actual numbers are, but all of this is just to say, the issue I see with those sort of predictive AI approaches today is the training set is small, it's biased, and it's full of a lot of noise. And my view is, if you use things like metformin and rapamycin to train your network and make predictions, guess what you're going to get out? Which is okay. I would be okay with the next generation rapamycin, but come on, guys, we can do better than that. So I think that's why we need a much larger, more robust and rich data set. Then these kinds of predictive AI tools become, orders of magnitude more powerful.
Yep. Well, and those data sets, like the Drug Age database, it is, as I understand it, it's agnostic to the quality of the study. So it's a hodgepodge of different styles of experimentation, different methods, even for the same animal. It's really tough to know that you're comparing apples to apples in a relevant kind of way.
Yeah, no, that's right. So we haven't yet really talked about the mechanics of the million molecule challenge. So Ora is a for-profit company. Ora obviously has an interest in developing new interventions and taking those forward to market. We'll talk a little bit about the strategy there in a minute, but there's also this sort of interesting community-based million molecule challenge. And so maybe you can talk a little bit about that, how it works, and what's happened so far.
Yeah. No, this is one of the, just one of the cool things that happens, to sing your praises a little bit, just having conversations with you. There's typically not been a time that I haven't walked out of a conversation with a better idea than when I walked in with. And I think this is one of those times where it was like, oh, we could do this, we could do that. And I think you mentioned the idea of like, well, what about sponsoring? Why couldn't people just get involved? And just like a light bulb going off, it's like, well, yeah, why not? Like, that's really cool. And so we started figuring out how to put the mechanics to it, how to create a store online. But ultimately, it's about citizen science. It's about getting people excited about longevity research and giving them the opportunities to do world-class science with scientists, get data back, and be able to talk about it. So it demystifies things, it broadens the community and makes a bigger tent, and it gets everybody talking in the same kind of language. I didn't know what we would end up with when we were starting this sponsorship out, but we've gotten to the point where the V1 database is out now, and it's been pretty remarkable. It's been cool to get everybody involved, but it's been really neat to see really kind of the quality of hypotheses that people generate. That's something that I didn't expect whatsoever.
Yeah. So again, just to make sure everybody is on the same page, for those of you who don't know about the Million Molecule Challenge, the idea here is that anybody can go to the Ora website. There's a list of interventions they can pick from. For now, it's FDA-approved drugs, although again, maybe that'll change in the future.
There's a couple hundred natural products.
So there's some natural products there now as well. And people can pick single interventions or two-way combinations, and then people can do higher order combinations through sort of a custom protocol, right?
Mm-hmm.
Okay. And so people can choose the interventions they want to test. There's a sponsorship, $100 per intervention, I believe, unless you guys have changed it. And then once people sponsor the intervention, it will get tested on the Wormbot, and just will go into the queue, get tested, and go into an open access database, which you were just referring to. Anybody in the world can get access to it unrestricted, right? Mm-hmm. So unlike even some of the academic open access databases, you don't have to jump through a bunch of hoops to get in there and actually see the data. So part of this is making the data available to the community so that other people can actually dive in and do interesting stuff with the data that Ora generates as part of the Million Molecule Challenge. I know this is sort of a weird idea, right? Because normally people think of companies as like wanting to hide all the data and generate IP, and I get it, that's part of what Ora needs to do, but the goal here is really to move the field forward. The reason why there needs to be a sponsorship model is because Ora's got to be able to actually pay people to do the work, right? Mm-hmm. And again, my philosophy is I would love, first of all, there's enough intervention space to have an open access component and a for-profit private component, period, right? And I would love to be able to give away 100,000 or 1 million molecule database to the community, because I think that would be super valuable. Mm-hmm. But we've got to pay for it somehow. And so this goes back to, this million molecule sponsorship model, comes back to my frustration with the difficulties getting discovery science funded. And, so I'm just going to put it out there. First of all, if you think this is a cool idea, you should sponsor a molecule. You should sponsor 100,000 molecules if you can for the Million Molecule Challenge. But look, guys, if we had started this 2 years ago when I started first talking about it, we'd have an open access database now with tens of thousands of molecules. Instead, we're spending money on stuff that's not accomplishing anything. So God damn it, figure this shit out so that 2 years from now, I can be here sitting and talking about the 100,000 intervention database that we've got that you guys are out there doing cool discovery science on. Sorry, that's my rant.
I like that we got the R rating for this YouTube video. Yeah.
The field would be so much further ahead if somebody did this and we had these resources available, that it just pisses me off.
Yeah, why aren't we further along? That is the major thing. It's the best analogy I've thought of through this time is if you got all the field together, it would be like digging in the dirt with your hands, or with, just like hand spades and stuff. Like, why haven't we brought in the backhoes? Like, why haven't we industrialized this and sifted through this space?
Right. And I mean, I get that people are going to argue about, well, why are you doing C. elegans? It's like, you got to do it something, right? You got to start somewhere. You're not going to test 1 million molecules in mice. And even if you could, I'm not sure that makes a ton of sense. So regardless, I think those are just excuses for not digging in and doing the important work. And it's time to stop making excuses. Okay. So back to the 1 million molecule challenge. So people can sponsor interventions. People have, and now the first version of the database is out with the first, I don't know how many interventions are in there at this point. It's a pretty small number still.
Yeah, there's a little under 100 right now. Okay. About a little under 80 single interventions and something around 12 or 13 combos.
Okay. And so anything interesting that you can talk about that's in that data set?
Yeah. This is something pretty cool. Like, I didn't expect us to have enough fodder to write a little paper and put it out from this initial data set, but we're going to.
Cool.
Yeah, so really fun. Some initial things that came out. First, we tested rapamycin. We tested some of these mTOR inhibitors of that rapalog and rapamycin flavor.
Yeah, let's talk about rapamycin real quickly, because there's a lot of confusion, I think, about rapamycin in C. elegans. And the dose response there is pretty important, like it probably is everywhere. And so actually, we didn't talk about how Ora is doing the 1 million molecule challenge. So when people select a molecule or combination of molecules to sponsor, that's at a specific dose, right? Do you remember off the top of your head what dose is being tested?
We've gotten more sophisticated with that as we've been going, actually. So we use a predictive calculator that predicts the aqueous solubility of the compounds, and then we use that to base our dosage off of. So compounds are tested at either 1, 10, or 50 micromolar, depending on the highest concentration we can test at.
Okay, and so are people given the choice of dose?
No,
or
we just test it
you
at
just
the
go to
highest
the
that we
highest
can.
dose. And what's the rationale for using the highest dose?
The highest dose, the received wisdom is that worms are a little difficult to drug. So you hit them hard so you can see an effect, and you can always back down a dose. If you test them too low on the dose and you don't see an effect, you don't really know what you've done.
Yeah, and I think this is, again, is an important concept for people to appreciate is anytime you're doing a large screen, you kind of have to pick your poison, right? You could test 5 doses for every drug, but then you'd be testing 5 times fewer drugs. Or you could test 1 dose for every drug, and then you can test 5 times more. And so you kind of have to decide, there's no right or wrong. You kind of have to decide what your tolerance is for false negatives, right? So missing things that could have an effect. If you're only testing 1 dose, it might have an effect at a different dose. And again, there's no right or wrong, but it sounds like Ora has settled on the model that we're going to test at 1 dose, but we're going to try to give ourselves the best shot at seeing an effect by going towards the higher end of the solubility profile. Okay. I think that's important to set the stage for rapamycin, because rapamycin is complicated because it has very poor solubility. So what have you guys seen? And then how does that compare to what's in the literature for rapamycin?
Yeah, so what we've gotten our hands on, so we've did, so first for the drugging for the plates and the wells and everything, we add drug right on top of these agar wells. It's basically a jello that the animals live on. It soaks up the drug if it's soluble. If not, it'll just accumulate on the surface of the media, and it can form this precipitate. So you get this white powder, essentially. With Rapa, you go from 1 to 10 to 15 micromolar. You're okay. The drug is getting solubilized. It's going into solution, and you're not seeing this precipitate. You go above 15 micromolar, we see this precipitate form where at 50 and 100, it's like a patch of white chalk over the top of the well. And if you look in the literature, the thing is at that 50 and 100 micromolar mark is typically where you see reports of lifespan extension.
Right. I remember 100 micromolar in the literature. Probably the first report.
And so in our hands with the Wormbot system, the animals are crawling over this like fortress of solitude.
That's exactly what I was thinking.
Palace.
So when the paper first came out on rapamycin in worms, we were working with C. elegans in my lab by that point and tested rapamycin, and I was doing those experiments, and I remember seeing those crystals. And like you just said, it reminded me of the Superman movie, right? And, the worms are like crawling over these rapa crystals. It did extend lifespan at 100 micromolar in our hands, but it's very difficult, I imagine, for a neural network to be able to resolve those images with these crystals on the surface of the plate.
Yeah, that's a challenge when you're adding the drug just over the food source also. It's not clear how that crystallization is obscuring the animal's access to the food. So they might get an extension through DR or something like that that's secondary to the mTOR inhibitor. Those are a couple of the really major concerns.
So at the lower concentrations, though, as part of the million molecule challenge, you have not seen lifespan extension from rapamycin,
No.
which is also consistent with the literature. Again, I think it also fits with the idea that for at least some drugs, you have to go to higher concentrations to get sufficient drug into the worms to have the intended biological effect. So you didn't see effects with rapamycin, but you have tested other mTOR inhibitors and seen effects, right?
Yeah. So at that 10 to 15 micromolar range is what we were testing the Rapa and Rapalogs at. Didn't see extension with any of those. This other compound, it's a dual kinase inhibitor, so mTOR and also a suite of PI3 kinases as well. That one at that 10 micromolar dose is the current leader on the leaderboards right now. It's about a 35% extension in lifespan.
Got it.
Even bigger, I think, than the effect that 100 micromolar Rapa has shown in some literature.
Got it.
So at that lower dose, it seems like it's even extending at least as well as Rapa is in some of those other publications.
Right. And this came out of the Million Molecule Challenge?
It's
Somebody
a direct
sponsored
one.
it?
Yeah, there's not been any published reports on that GSK compound prior to.
Interesting.
Yep.
And then I know you can't tell us the molecule, but Ora has at least one other mTOR inhibitor as well, right?
Yeah.
That extends lifespan more robustly than rapamycin in worms.
Yep. Yeah, that just kind of just goes to the question of, even for the gold standard target,
right,
we don't know the best molecules to target that thing.
Right. And that there are probably better things out there, right? I mean, we know that at least in worms, and I think it's almost certain to be the case in mice as well, that if we could test a library of mTOR inhibitors for their effects on longevity, we would find things that are better than rapamycin. Why has everybody studied rapamycin? Because that's what was tested first. And it's the mTOR inhibitor that there's the most known about. No reason to think it's the best one. So I think there are real opportunities here. Talk about low-hanging fruit. I mean, again, this is just something obvious that really should have been done by now. Nobody's done it.
They'd have laughed you out of the study section if you wrote a grant trying to, I just want to screen every mTOR inhibitor. Like they would not get it. They wouldn't see the value there.
Yeah. Okay. So that's come out. Anything else? Have there been other things that increase lifespan?
Yeah, some of the other ones. So aside from that GSK molecule, the two other tied for second moleccules are natural products.
Interesting.
So one compound, berberin, and another one
probably many people have heard of. Yeah.
Yep. That one has that's an
natural
interesting
product, metformin. Some people say.
Yeah. It seems like it's impacting through the mitochondria, and there's something about that mitochondrial function story that impacts whether it's successful or not. So berberin's one, and then this other one called it's punicologan. I'm almost certain that I'm butchering the name of it, but it's a compound found in pomegranate.
And people can go to the Million Molecule Challenge database and look for themselves, right?
Yeah,
so this is
the database
Ora
is there.
Biomedical website. You can go there, check it out, see the data that's been collected so far, sponsor a molecule while you're there, and then get your own data. And so in addition to putting in the database, Ora is returning the data to the sponsor, right? And so they will get that information. Do people have to share their data in the database?
No, they can opt out of being in the database. They can just work with us. We do want to talk with people as they are sponsoring interventions and getting hits and stuff like that. We want to just, give them some context around those results. If you get one hit in a C. elegans study, you don't want to go rush off to your local venture capital firm and get $10 million from them to spin up a company. You should repeat the study first. You should do a dose response. You should better understand it. And we're the right team to help you out on that pathway.
Cool. Okay, so I think we're both very optimistic that in some way, Million Molecule Challenge sponsorship, additional funding, we're going to get this done. And I think to me, this is just no-brainer. This will have an immense impact on the field. I don't know if it's going to be the most important project in the field but I think there's a chance, right? I think that we really need to find new interventions. Nobody's out there looking for them at scale. So I hope that we'll get there in the next few years, and I won't be banging my head against the table saying, we could have been done by now if somebody had stepped up. All right. So we're going to get there. Okay. So I know, people ask about contract research, and that wasn't really the plan going into Ora, that, Ora would do experiments for other people. Million Molecule Challenge is kind of like that in the sense that we're doing experiments for the rest of the field, or for the public, the community. But I know Ora has also started to think about contract research a little bit different. Do you want to say anything about that, and how your thinking has evolved there?
Yeah, sure. As we were spinning up Ora and getting things off the ground, we found ourselves in a pretty challenging environment for fundraising. We just closed our seed round a few months ago. That's something a lot of groups weren't able to do, but we were having to think about every way that we could be scrappy. And as a platform company, utilizing your platform for contracted operations is an obvious other offshoot for that. So that's where we were starting to go with it. We've gotten some good contracts come up, some great partners, and we're looking at different ways how we expand that and move that forward. I see contract research being a bootstrap we can use to move ourselves forward. And I think everybody wants to say that their last raise might be their last fundraise, or at least that's what they want to tell their investors at the time. But by doing this kind of contracted research, we're going to be able to self-finance ourselves to the point of pushing out some of these first assets, we hope, from our internal development pipelines.
Okay, and that brings up the next question, which is, it's great to have a lead in worms. How do you get that to market?
Yeah. So you got to go into mammals. You got to move in eventually, and that's what we've been trying to solve also. There's a really interesting opportunity that's starting to emerge where I think Ora Biomedical is going to be starting up our own vivarium, and it's going to be a very special kind of vivarium. It's going to be specialized around identifying longevity interventions that work particularly well in aged animals in the most impressive manner.
And here we're talking about mice.
Mice. Yeah. So moving into a mouse system, utilizing some of the mouse models that are out there, some of the kind of gold standards right now in the field, but really aiming at interventions that can improve aged mouse health.
Yeah. And lifespan. Hopefully.
Yeah. Healthy lifespan. Yes.
Yeah. And so how does Ora prioritize which interventions to move into mice? Because, again, this is one of the challenges, if you can screen 1 million molecules, you're going to have a shit ton of good candidates. Yeah. How do you pick the ones that are worth taking forward and moving into mouse models and then beyond that?
Yeah. We don't have a great decision procedure just yet. We're trying to be a little bit slow rolling to see what the most impressive thing we can identify is. But at the other hand, we want to move forward and we want to put some points on the board as well. So we're getting pulled in a little bit of two different directions there. But we do have one asset that we definitely want to put into a mouse study as soon as we can.
Yeah. And I guess I would say, one obvious factor would be how big is the effect, right? If you get this thing that triples lifespan, you're going to be pretty excited about it. What do you know about it? Is it an mTOR inhibitor, for example, right? But also, I think what you were alluding to is you want to start moving forward. And so some of this may just depend temporally on when you get the hit, right? Yeah. Get the first thing into mice, figure out whether it works there, and then you can move forward. So how are you thinking about after mice? Let's say you do that, you show that your molecule or molecules can increase health span metrics, hopefully increase lifespan in mice, then what?
So scooping up that IP and planting our flag around that IP so we can protect it, that might end us putting us into some different disease indications to show that, it's aging and these different diseases of aging where this intervention has its efficacy. The other part might be pushing us more into just other kind of disease studies as well. So this is getting to the point of, do you want to go after an FDA approval for a disease indication, or do you want to do something like what, some of the other companion pet groups are trying to do, which is create an intervention to go at a pet market? I see those as kind of the fork in the road there.
Yeah, and I think what you're getting at is a challenge that probably every biotech company in the field that is moving into clinical stage is dealing with, which is how do you approach the regulatory environment? Because really, unless it's a natural product combination, and that's on the table for Ora too, right?
It is.
You may find combinations of natural products that have very robust effects where you don't need to go necessarily through the FDA regulatory process, but let's just assume this is a new drug. How do you approach drug approval through FDA in the context of a geroscience intervention? And so I think what you alluded to is, the approaches that people are thinking about, and there's going to be, I think, movement in this space where people try different strategies, but there is not one obvious right strategy for how you take a geroscience drug to market. And that's an evolving space that will change over the next few years. So we've covered a lot of ground. I think hopefully we've given the viewers a better feel for Ora Biomedical, what Ora is all about, why you and I at least think this is probably one of the most important areas in the field right now. Huge potential. Hopefully encourage some people who maybe didn't know about the Million Molecule Challenge to participate. And so with that, I just want to thank everybody who has stuck with us for watching this episode. I hope you found it informative. As always, if you have any comments or questions, please leave them below. If you're not already a subscriber, please consider subscribing. And I hope to see you next time on the Optispan Podcast.